One of the places that that's going to be useful for us to solve exponential equations is one place is finance. If you are if you have a savings account and your interest is calculated compounded interest on your savings account, then you're going to use an exponential, or the bank is going to use an exponential equation in order to calculate that. If you have bacteria growing in your petri dish in biology, it's going to grow at an exponential rate. If in physics you are measuring the decay of radiation, it's going to decay at an exponential rate. And all of those, so we're going to start with exponential growth. I'll start with growth. The growth of your interest, the growth of the bacteria is going to look something like this. This is at 0 time. This is our time here. This is our value here, whether it's our interest or our amount of bacteria. So this is where we are at 0 time, and then this is where we are at some time in the future. And this pattern is going to look something like this. So at any point in the future, the value at any point in the future is going to be the value that we began with times e to the kt power, where k is a constant. It could be, if it's in finance, that constant is referred to as a rate. So that's your rate of interest, or that you are making on the savings account, or the rate of interest that you are paying on the loan, either one. So this is growth. When it is a growth, that k, the rate, is greater than 0. The other type of exponential equations we're going to deal with will be a decay. It's going to look something like, draw me a separate picture. It's going to look something like this. Again, this is 0. This is some point in the future. Sometime in the future, this is our value, whether it's the amount of radiation, or, so that's a sub 0, and this down here is a sub t. So this decay is going to follow this same pattern as the growth. The only difference being, remember I said if it's a growth, your rate is going to be greater than 0. If it's a decay, your rate is going to be less than 0. So it's the only difference, but they're going to follow this same pattern right here. A sub t is equal to a sub 0 times e to the kt power. So let's look at a couple of examples, well, the practice problems for this. And I'm going to do the last practice problem first, and then I'll come back to the second one. And the last practice problem is rabbits, which reproduce exponentially. So the number of rabbits increased exponentially. At first, there were 400. And 3 years later, there were 1,600. So here's my chart that shows my rabbits. 3 years later, I started out at 400, and I ended up at 1,600. 3 years later, right here. Something like that. And the question is, how many rabbits do I have after 10 years? So the data that I've been given here, the 400 at the beginning and the 1600 at 3 years later, will tell me, will allow me to calculate the rate of growth, exponential growth. So remember, so a sub 0 is 400 and a sub 3 is 1600, but you'll remember from our pattern that a sub 3 is going to be a sub 0, which is 400, times e to the 3k power. 3 being the time, 3 years, and our rate is what we don't know. So we need to calculate that. Notice here though that a sub 3 is also 1600, so we can substitute that. So 1600 is 400 e to the 3k power. Get rid of our 400 by dividing because we're multiplying. So 4 is equal to e to the 3k power. So that means if I write this in logarithm form, remember, that means this is base e, so I'm going to do natural log. So this is my base. So it's the natural log of 4, because that's the antilog, is equal to 3k. So k is equal to the natural log of 4 divided by 3. Another way you can show this also is if I just ask, how can I write 4 with a base e? It's the same process. I'm just showing it a little different. So if I do 4 natural log, 4 is e to the 1.386 power, and that's got to equal to 3 to the k. So I have rewritten 4 with a base e, and I already had e to the 3k. So if the bases are the same, then those exponents have to be the same. 1.386 has to equal to 3k. Divide by 3. K is equal to. I'm going to get the same thing over here because I'm going to take the natural log of 4, which is what I have right here, and I'm going to divide it by 3. And I'm going to get k is equal to 0.462. That's what I get over here, 0.462. So 2 different ways I can show this. I can either take the exponential equation and write it in log form, or I can take my 4 and write it as a power of e, and then my exponents have to be the same. Either way is fine. So now I can better describe what's happening in this particular puzzle as a sub t is equal to 400 times e to the 0.462 t power. So now I can find how many rabbits there are at any point in time. 10 years later, which is what I'm fixing to do because that's what the puzzle asked for. I could find it at 15 years later. I could find it at 100 years later. Once I have the pattern, I can fill in any points I want to. But we are actually looking for 10 years later. In 10 years, if I multiply that 0.462 by 10, I get 4.62. So in 10 years, I'm going to have, go ahead and write that, e to the 4.62 power. Remember, e is that special number, there it is, 0.462, that's like, nope, I need 4.62. Raise e to that power. We get 101.494 And when I multiply that by 400, 40,597 rabbits. That's a lot of rabbits. I'll close my parentheses right there. Alright, so like I said, once I have discovered the rate of this growth, at any point I can find out the value at any point in time, just as I did here. Alright, so this one was growth in science, I guess, animal studies. Another place where this is going to be used is in your finance, and so the practice problem B has to do with finance. In finance, the pattern is the same, but in finance we call the pieces by a little bit different name. Remember, I had a sub t is equal to a sub 0 times e to the kt power. But in finance, we can leave it a sub t, I think. Let's see what they say. Yeah, a sub t. But a sub 0 is usually called the principal, so they'll use the p for principal. And e to the k is usually your rate of interest, rate of return. So we use an R instead of the K. But again, it's the same pattern, just specialized for finance. In this particular one, it says Mary had $980. So her principal, to start out with, was $980. She is earning 7% interest. So her rate is 0.07, because that's 7%. And it wants to know how much money did she have at the end of 9 years. So our T is going to be 9 in this case. So we're going to use our pattern here. So a sub 9, the amount after 9 years is going to be what we started with, the $980, times e to the 0.07 power times 9 years. So 980 e to the 0.63 power. So I'm going to take my calculator, I'm going to raise e to the 0.63 power, so you need to figure out how to do that on your calculator. And then, well, I'll write it here. 980 times 1.878, got an 8. And so, in 9 years, 1.878 times 980, she should have $1,840.44 in 9 years. So again, you're going to want to remember your pattern here that you're going to apply to these exponential growth and decay puzzles. All right, I think that's it. Thank you.